So thanks everybody. I'm excited to be here for the inaugural ANSS seminar. We're going to talk about NEIC's newly released finite fault modeling package called WASP. The finite fault is one of the many available products on the USGS event pages, and the people in this meeting, I am very certain, are familiar with these products, but in case this presentation gets viewed by anyone else in the future, just humor me for a second while I go through some background information about the product. So the USGS produces three main products related to earthquake source characterization. So that's the origin, location, and time, the moment tensor, which is basically a point source approximation of the event size and the fault orientation, and the finite fault model. Generally, we produce a kinematic SliP model that shows the timing and distribution of SliP. The USGS also produces impact products that are informed by these source characterization products. So on the right, we have shake map, which is an estimate of the location and intensity of shaking, which is in turn used to estimate losses from the earthquake in the pager product on the left. And the origin and moment tensor are used to make that preliminary estimate of the shake map and pager products. And they're also used as input to the finite fault model. Finite fault model is one of our slowest products. It generally takes about an hour and a half to complete. And once completed, the SliP dimensions from that finite fault model are used to update the shake map shaking distribution, and then after that, the pager estimate. So what exactly is the benefit of a finite fault model to earthquake response? You can see pretty clearly that distinction in these two earthquakes from 2021 in China, a magnitude 5.5 on the left and a 7.3 on the right. Small to moderate earthquakes like the one on the left can be reasonably approximated by a point source. You can see that shaking is distributed basically symmetrically in all directions. And that is certainly not the case on the right-hand side of this slide, where large earthquakes can occur over a much longer fault length, and earthquakes of that size are very poorly approximated by a point source. You can see in this image where the hypocenter of that earthquake is, and that shaking is distributed sort of linearly along the fault plane and not just concentrated at the location of the hypocenter. So another good example of this is the magnitude 7.8 main shock of the Turkey sequence, which in this rupture mapping by Nadine Reitman and others, you can see ruptured over 300 kilometers of fault length and would be very poorly approximated by shaking derived just from this hypocentral location, which is even off of the main faulting area. So in summary, an earthquake's local impact is much better approximated by the distance to the ruptured part of the fault than it is to the hypocenter or even the centroid. So estimating that SliP distribution is really critical for estimating ground shaking, loss, structural damage, tsunami generation, you name it. I'll also note here that finite fault models have value beyond earthquake response. So robust models of earthquake kinematics and SliP distributions are important for studies of earthquake statistics or magnitude scaling or laws or studies of large earthquake rupture processes, etc. So at NEIC, although our main focus is rapid response and contributing to those products that I showed, we know that our models can be used in studies for the kinds of topics that I just mentioned. So we try to take steps to update our models in the post-response timeframe when feasible, and the software that I'm about to demonstrate can certainly be used in a research timeframe rather than just a response timeframe. So how do we turn earthquake observations into a finite fault model? First, we need to define the fault orientation. We need a strike, a dip, and an average rake. And we usually take that from a rapidly computed moment tensor solution. For earthquakes that are complex, like the ones that you see on the right relating to the 2023 Turkey earthquakes, those moment tensors are kind of just a starting point, and then we can create more complicated fault structures. For rapid response, we generally end up posting a single planar fault with a strike and dip that's pretty similar to the moment tensor. And you make the fault dimensions larger than the area that you expect SliP to happen to make sure that you capture the entire slipped region and that SliP can diminish to 0 at the fault edges. So we create this planar fault and divide it into smaller rectangles, which we call subfaults, and then use that to invert for the timing and amount of SliP on each subfault that best fits our waveform data. And we use a nonlinear inversion method to model SliP amplitude, rake, rupture time, and rise time to find the solution that best fits the earthquake observations in the wavelet domain. So now getting to the meat of this talk, NEIC has been performing finite fault models as part of routine earthquake response since late 2007. Since then, we've made many improvements to the code, and as of this month, the finite fault software that we maintain is available as an officially released software, meaning it's gone through a full USGS software review process. We call the software WASP. It stands for Wavelet and Simulated Annealing SliP. And the code is based on the approach by Chen-Ji and others published in 2002, which was developed in Fortran. And in WASP, these Fortran scripts are wrapped in Python, and we use a simple command line interface, or CLI, to interact with the software. So first, I'd like to just take a moment to acknowledge the co-authors of the software, Pablo, Heather, Diego, Sebastian, Will, and Kirsty, who've been really instrumental to getting the software where it is for publication. So what can we do with this software? WASP currently accommodates observations from teleseismic broadband seismometers, local strong motion accelerometers, local high rate or static GNSS. Here in the picture, you're seeing high rate GNSS waveforms. Also can just use static offsets, and downsampled interferograms from InSAR. Software installation process is made very clear in the documentation, as you can see on the left. And this morning, I just reran the installation to remind myself how quick and easy it is. And if you follow the instructions in the documentation, you should get this nice little WASP installation completed to know that everything is working. This makes sure that you have a new conduit environment specific for WASP and all of the necessary dependencies. It compiles all of the Fortran for you and just downloads all of the external files that are needed to run all of the calculations. The WASP CLI, which you can see here, has 4 main commands: manage, model, plot, and process. And with the exception of a few modifications that I'll show that we suggest doing manually, these commands include everything that you need to build a finite fault model. And here I'll just zoom out. You can see the help messages for these 4 top-level commands showing all of the available subcommands. And it's not important that you see all of these in detail, but some of them will come up in the rest of the talk as I walk you through a demonstration. So the official release of WASP includes a Jupyter Notebook tutorial to walk the user through the 2015 magnitude 8.3 Iapel, Chile earthquake. And for the next portion of the talk, we're going to partially go through the tutorial and kind of get a feel for the software design and using the CLI. I'm going to skip over the part of the tutorial that goes through the installation and instead go straight to getting all of the data. So the tutorial data is available in a science-based release, and we've used the EAPL earthquake because it has all of the data that is supported by WASP. So that's teleseismic observations, strong motion accelerometer, GNSS, and InSAR. And it can just be downloaded with this code and organized the way that it needs to be for use in WASP. Once you have the data, you're ready to run the initial auto inversion. The auto inversion estimates a solution for both nodal planes in the moment tensor, and it's up to the user to determine which of those is the preferred solution. Sometimes you'll notice on the NEIC website, we occasionally don't know which is the preferred orientation, and we'll post two solutions, but generally it's fairly obvious. So starting with this auto inversion, first it asks you for your path to WASP to make things simpler. And if you run the WASP manage show config, it will show you all of the paths to all of the files that you need. You can make sure they look good. And then finally, here I've just asked it to print the moment tensor that we're using. So you can see that this is a required input in CMT solution format that has information about the hypocenter location, centroid location, and all of the components of the moment tensor. The Python call to that auto inversion that I talked about that will run a solution for both nodal planes can use any of the available data types. You see them here: body waves, surface waves, strong motion, continuous high rate GPS, static GPS, and InSAR. In this initial run, we're going to do what normally happens in NEIC response at this point, which is start with just teleseismic observations, which are normally currently what we get first. So you can see we'll set this up as a WASP model run. You give it the path to the moment tensor, the path to where the teleseismic data is, and then tell it you want to run the solution with both body and surface waves. So you'll see a lot of output when the process starts. It will write a lot of files that are required for generating the solution and do some data processing. And then it'll start running through 250 iterations of in the simulated annealing. And at some point here, you'll see that this countdown or count up that's going from 1 to 250 will be interrupted by the second nodal plane finally getting up to speed, and you'll see a second set of counting up from 1 to 250 sort of interspersed there. So now I'll scroll a little bit faster and get us to the end of these 250 iterations. So once the 250 iterations are complete for both nodal planes, WASP creates default plots for the SliP distribution and for the waveform fits that you'll see here in a minute. And obviously, I ran this well in advance of this talk. This usually takes about 10 minutes to run. You'll see here a summary of the solution. See the end of kinematic modeling, and then we'll start seeing output related to plotting of all of the default plots. So that's the end. This one has been a successful automatic run, and now let's look at the results. So here are the results from that initial automatic inversion. I've already chosen the preferred nodal plane to be the one that's consistent with the megathrust orientation. The opposite nodal plane just has no does not make geophysical sense in this region. So here on the left is the source time function. It's roughly a 2-minute rupture for magnitude 8.3, which is believable enough. And the SliP distribution is kind of a mess. You can start to see where you think SliP is relative to the hypocenter, which is here. So maybe this was a slightly unilateral rupture to the north. But there are two initial thoughts that I have when looking at these automated results. One is that either the fault area that WASP calculated is not big enough. And I say that because there is SliP going all the way to the down dip edge. There's SliP going all the way out to the northern edge. And we want SliP to fade off to 0 to make sure that we capture the whole thing. So maybe the fault area isn't big enough. Or maybe there's just some wonky data in this inversion, and what's happening at the edges is trying to fit noise and trying to fit bad data. And if you do enough of these, you'll start to learn that the latter is pretty common. So I'll just show you some of the plot of the love wave fits. So we're going to start with that, like option 2, that there's some weird data in here. So in the love wave fits, the observations are in black, the synthetics are in red, and these are pretty decent fits. Nothing is sticking out as horrible. Sometimes you see stations that have bad metadata, and so the amplitude of the observations will be many orders of magnitude off, and that's sort of a very obvious problem that needs to be taken care of. But if you look closely, I pointed out 4 stations that look not so great. And so if we remove or downweight these stations, we expect the SliP distribution to clean up a little bit. So here's the part of the tutorial where the user learns how to delete stations, or my personal preference, just downweight the stations to 0 weight. And I prefer to downweight rather than, well, I'll delete if, the station has bad metadata and there's no chance that it's ever going to fit the model. But generally, I prefer to downweight because sometimes those poor fits will be improved as you start to learn more about the model, and you can add them back in. And if you downweight, you still get to see what those fits look like and see if they're starting to fit any better. So in order, here I've just put out the WASP manage modify dictionaries help function. So you can see the modifications that we make are either delete or downweight. And then you specify the data type. So that's the same, body waves and surface waves that we're dealing with. So here's that a little bigger. So you can see the commands that I'm using. You use one of these station channel flags for each of the stations and channels that you want to downweight. In this case, I'm downweighting just the surface waves, and I'm downweighting station Hope in both Rayleigh and love waves, station ASCN just in love waves. And of course, I didn't show you any of the fits for PSH or Rayleigh waves, so you're just going to have to believe me that these were good choices to make based on the plots that came out of that initial inversion. We commit these changes using the command wasp manage update inputs, and then you can run another inversion right away. But first, I'm going to show you some other really typical modifications that we generally make and how you can accomplish that yourself using the software. So commonly, we'll make modifications to the fault orientation and dimensions. This is done in a JSON file called segmentsdata.json. Here's an example of the one that came out of this automatic inversion for EAPL. And it's best just to go into your favorite text editor and edit this directly. But there's a lot going on in this JSON file, so I'll point out some of the critical parameters here and what they mean. First, you can see how many fault segments there are in the model. In every auto inversion, there will just be one fault segment. So like you see here, there's only one set of brackets. So this is just a single segment fault segment model. And the segment will have the orientation of the input moment tensor. So you can see here the dip, the rake, and the strike. And I'll also note that the rake is allowed to vary. This is just an average, a target average rake that the model is shooting for. How much it can vary is denoted in a separate JSON file that I'm not going to talk about today. Usually the value doesn't need to be changed. Sometimes for very complex ruptures, it does need to be adjusted. Next, we see how many subfaults there are in each direction. So in this case, there are 9 rows of subfaults along dip and 23 columns of subfaults along strike for a total of 207 subfaults. The code is designed to aim for a number of subfaults in the low 200s in order to keep the inversion computationally feasible. So it'll determine, how many and then assign how big those faults are in order to cover the area that it thinks the rupture will take. Those dimensions in the dip and strike direction are denoted here as delta dip and delta strike. And in this case, it's come up with some pretty long, wonky numbers to get to that target 207 subfaults. So these subfaults are about 18 kilometers by strike and 15 kilometers by dip. And then finally, which subfault represents the hypocenter? So here, hype dip and hype strike means that the hypocenter is in the 5th row along dip from the surface and in the 9th column along strike in the strike direction. And I'll show you what that looks like visually in a second. But you'll notice originally that the hypocenter is not exactly in the center of the fault overall. It in the 5th row is in the center of the 9 rows along dip, but in the 9th column is not in the center of the 23 subfaults along strike. And that's because WASP has interpreted that this is likely a slightly unilateral rupture. It's not always perfect at making that estimate. And for those reasons, that might be a reason why you need to modify this, this file. So here's just a visual image of how you can imagine what this file is telling you. So in this grid on the left showing a fault perpendicular view of the modeled fault, in this example, we have 15 subfaults along strike and 8 subfaults along dip. And this red line indicates that it's the up dip edge. If the rupture is bilateral, like this rupture in blue, you would want your hypocenter to be basically right in the middle of the grid. So in this case, column 8, row 5. However, if you have a strongly unilateral rupture and like the yellow rupture here, putting the hypocenter in the middle of the grid is not going to work, or at best, you're going to have a really, really long fault with absolutely nothing going on one side. So in that case, it's preferable to put your hypocenter coordinates close to a corner, in this case, column 3, row 2. So here's an example of an automated run I did recently that's incorrectly identified this as a unilateral rupture and shoved all of the SliP all the way into this corner. So by making modifications to that hypocenter coordinate in the following run, I was able to get the entire SliP distribution more or less centered on my fault plane and allowing us to know that we captured the full rupture asperity. So in subsequent iterations of this EAPL model, I'm just going to make a few subtle changes to this segments data.json file. And really, I just sort of cleaned it up a little bit. I made these have made the subfaults 15 by 15 kilometer squares, which I just think is easier in my brain to work with, and basically left everything else the same. I made very slight modifications to the strike just to align it better with the known strike in that region. So one other iteration that I make pretty much in every model is a temporal shift. Temporal shifting is a critical early step to account for poor velocity models. So basically, WASP calculates the arrival time of these different phases based on a one-dimensional velocity model. And so often that results in there being a temporal offset between the observed phase arrival and when WASP thinks it should arrive. And because of that, you get fits that look like this on the top, where the observations are in black, the synthetics are in red, and they look similar, but they're not aligned. And that's a velocity model issue. So we correct it by either doing an auto shift that performs a cross correlation to align the waveforms, basically trying to align the minimums and maximums. But sometimes that doesn't always work right, especially when you have some more complexity showing up in your waveforms. And so we also provide a manual shift option where users can input a specific value in seconds that they want to shift their observed waveforms by to align with the synthetic waveforms. So let's just assume that I've already made all of those changes in the Jupyter notebook. And with all of those changes in place, we can rerun the inversion. This time, instead of using the auto model option, we will use the manual model option, which you can see here. And again, we're just going to include the body and surface waves because that's all that we've dealt with so far. Here, I'm just showing the tail end of what comes out in your terminal window. So here are the plots, and we'll skip ahead to results. So this result, I think, shows a lot of improvement. I've included the LUV waves again here, and you can see those 4 stations that I downweighted to 0 show up as dashed lines, but you can still see how they're fitting. The SliP distribution has gotten a lot less messy, but the SliP patch still kind of extends to the edges. We could certainly increase the number of subfaults along dip and along strike in the segments data.json file. But in the next slide, we're going to start adding local data. And I know from experience that local data tends to tighten up SliP disparities. So we're going to skip the extension of the fault and move right to adding local data. So ideally, in response, we will get access to local strong motion and GNSS data in real time. And there will hopefully be a future where we get that data before we even get teleseismic data. Currently, we generally get it after we make our initial model. So that's what I'm mimicking here. To add local waveform data, the data has to be in SAC format with certain required header information, and you can see all of that information in the software documentation. So the process for adding strong motion and high rate GNSS data is the same. So I'm just going to show strong motion data here. It uses the subcommand manual model add data. And if you point it to the location of the new data and the data type, it takes care of the rest. So here it's going to output a bunch of information to the terminal describing what it's doing. So it's processing the data in this case. And then here, using a 1D velocity model, it is calculating the local Green's functions required for the inversion. Depending on how big your region is and how far away your stations are, calculating local Green's functions can certainly take a while. So we're going to skip ahead to the results of this included local waveform data and see some nice figures. So in the left side here, you'll see fits to the high rate GNSS and the accelerometer data up here. So in both of these figures, each row is a separate station, and the columns are the east, north, and up components, respectively. So note that the moment rate function really hasn't changed a ton as we're making all of these modifications, but the SliP distribution is changing significantly. It's getting a little bit tighter, the maximum SliP is increasing a little bit, and SliP is not going as deep as it used to with just the teleseismic data. And so in the interest of time, I'm going to basically repeat the process that we just did for static data this time and include just static GNSS vectors. Sometimes these are overlapping stations. Sometimes more often than not, we have static GNSS data from many more stations than we have high rate GNSS data because we can include lower sampling rate stations as well. So here you'll notice that when we include GNSS data, the GNSS vector fits with the observed offsets in black and the synthetics in red get automatically added to the plots that are created from doing this manual model. But you'll also notice that the SliP distribution changes a lot. Geodetic offsets are really sensitive to where the most SliP is coming from. And so you can see that here in this like massive concentration of SliP. We'll also note that the maximum SliP in this plot has almost doubled when I added the GNSS static offsets. And since our color scale goes to white at around 10% of max SliP, there is likely still SliP in these regions where we were seeing it before. It's just not making up the main part of the SliP disparity anymore. And then finally, I'll add the InSAR data. Hopefully this is large enough for you to see on your screen. This left image shows the outline of the modeled fault area here. And then these are downsampled InSAR line of sight displacements. And they're downsampled in a way so that we have more points where more is going on. So we need more points to describe the pattern. And then here in the center, we have the model estimates of those line of sight displacements. And then on the right, the misfit, which is more or less zero everywhere, suggesting that it's fitting the data pretty nicely. Here, the model's maximum SliP comes back down a little bit to about 8 meters. So we're seeing a better consensus of all of the different data types. And it partially because of that lower maximum SliP and how the color scale is represented, and partially because of where the InSAR data is showing SliP, we're getting this like long extended, along strike SliP area. So this is where I'll leave you in terms of the EOPEL example. If you've seen our 2022 SRL paper about improvements to NEIC finite fault modeling that included EOPEL in the analysis, you'll notice that this is not as nice looking a model as the one that we published in that paper under a like research timeframe. If this were an actual model that I was getting ready to post, there would be many more iterations of continuing to go through the data and throw out or downweight bad data, continuing to adjust the model orientation. There's a great command in the WASP CLI that allows you to vary, strike, and dip and compute a whole bunch of like a suite of models all at once and see which one fits the data best. Because sometimes your fault just needs to be, rotated and dip a few degrees and will suddenly fit the data significantly better. So I really encourage anyone who's interested to go through the Jupyter Notebook tutorial and play around until you get a solution that you're happy with and make all of these modifications that I talked about multiple times as you go through. I will also mention sort of somewhat unrelated to the EAPL example, one of the advanced features that we include. So WASP relies entirely on planar faults, which is a fair limitation of WASP for characterizing more complex ruptures. However, it can model two or more planar faults that are either connected at the fault edges or are completely independent of each other. So I'll just show you a quick example of what that might look like. So if you have a more complex earthquake, you can see how you might begin to do that with this software. So first, I'll bring back that segments data.json file. Here is an example where there are two fault segments. Now you can see these two different sets of brackets with a lot of repeating information, but now they can have two separate strikes and dips. And then also down here at the bottom, there's a connections field that asks the user to specify how, if at all, these segments are connected to each other, which would allow spatial smoothing across that boundary. So if you, for example, connect faults along strike, but they have different strikes to mimic a curve in the fault orientation, you'll specify to the code that they are connected at those edges that SliP can be smoothed across that interface. Here's an example of how you might use multiple segments to approximate, in this case, a progressively dipping fault. So in the right-hand side here is a schematic. Let's say this white dashed line is the actual fault, and it's getting progressively steeper at depth. So here, segment 1 in gray is the segment that contains the hypocenter. There's a shallower planar segment above that dips at a shallower dip, and then this blue segment at the bottom dips at an even steeper dip than the hypocenter plane. And then on the left-hand plot, this is just showing how you would specify the location of the hypocenter relative to all three planes so that WASP can interpret where these planes are located in space. So in this case, on the gray segment, segment 1, it's pretty simple. The hypocenter is 6 along strike, and I think that's 4. It says 4 along dip. So that's what would be entered into the segments data.json. In fact, for all of these segments, the hypocenter is 6 columns along strike, but the hypo dip is a little different. So referenced to the blue segment, the hypocenter is at coordinate -5, and the hypocenter dip coordinate for the pink segment is 7. Yeah, 7. So those are how you would count the distance to the hypocenter and enter that into your segments data.json. It's a little bit complicated, but once you do a few, it gets to be pretty second nature. So as we creep up on having about a quarter of the hour left, I'm just going to go through some recently published works that have included analysis done with the WASP software, just to demonstrate how this software can be used in a more research-oriented way, rather than operational response framework. So first here is a paper led by Will Yeck that included modeling of kinematic rupture of the 2023 Morocco earthquake, which showed rupture on a blind thrust fault, and we used teleseismic and InSAR observations to make that estimate. Generally, at NEIC, we perform finite fault models for earthquakes magnitude 7 and larger. Magnitude 6.8 is kind of pushing the bounds of what teleseismic data can do, but because we have the availability to include these other data types, we're able to get a robust model. In this next paper, that was also led by Wilyak, caused us to make some neat modifications to the software that are available for your use. So we modeled concurrent rupture of 2 faults. So the initial rupture was on an offshore interplate fault, followed 11 seconds later by a dynamically triggered rupture on an intraplate fault that was 30 kilometers away. And so in this case, you can imagine that that segments data.json file that we talked about would list 2 segments and have no connections because these are disconnected faults. And this was interesting scientifically because the first rupture that's shown here in the source time function in pink was very slow compared to the second more impulsive onshore rupture shown in purple. And so that rupture overlapped temporally, and we had to modify WASP to be able to consider the summed contribution of both of those ruptures in our waveform data. This next paper summarized the source characterization of the 2023 Turkey earthquakes. This sequence tested WASP in a couple of ways. First, it required us to use multiple planar faults to approximate the curved along strike structure of those faults with 3 planar segments for each of the 2 earthquakes. And because our models normally include just a single planar fault that's roughly in line with the moment tensor, in this case, we've now added a script to WASP where you can see how the contribution from each of the planar faults contributes to the total moment tensor to give you some sort of confidence that these orientations and the amount of SliP that's being put on them is consistent with the independently estimated moment tensor. And then finally, this paper, which was out in 2022, was the first that showed our inclusion of these local data sources and demonstrated that while teleseismic only models seem to resolve the moment rate function pretty well compared to joint regional and teleseismic models, which is what you're seeing here in this right-hand column. So the gray moment rate functions are for teleseismic only inversions, and the blue ones are for joint teleseismic inversions. So sort of the general main aspects of those source time functions are pretty similar for both inversions. However, the inversions in terms of SliP, there's a significant difference. So on the left here are 3 different earthquakes computed with just teleseismic data, and on the right, those same earthquakes showing both teleseismic and regional data in the inversion. And you can see that the inversions that have all of the data types here on the right are showing slightly more compact models with higher maximum SliP and smaller overall rupture dimensions, which may in the future contribute to our ability to revise things like magnitude scaling relationships. So with that, I will wrap up and advertise that WASP is available on the USGS GitHub for community use and comments and contributions. I've linked the official release version 1.0.0 and also the main branch. This is unreviewed, but for bleeding edge developments. So should we have any issues that need to be taken care of. So with that, I will stop sharing my screen so I can see people, but I can share again if need be. So thank you.